Okay, so part of this internal you are going to have to justify what's being made. And for that you're going to need to know some tests for different species, so different ions or different molecules. And you've actually met most of these before, but I just want to record this so you've got them all together in one video. So what might be being made if you're working with Fe2+, is it could be turning into iron metal, or it could be turning into iron 3 ions, because Fe2+ can be both an oxidant and reductant. So it could become Fe3+, or it could become the element again. Okay, so it could be oxidized or it could be reduced. So if you're working with Fe2+, you need to be able to prove which one is made. Well, iron metal is normally pretty obvious. It's specks of grey or black in the test tube or in the beaker, because it's a metal, so it will form metallic bonds and precipitate out, basically. And you often see that with copper. You often see that pinkish, brownish solid being formed, and you know that copper 2+ has become copper metal, or you infer that. But what I want to show you is how we prove that it was Fe3+ that was being made, if that's a possibility. So Fe3+, for a start, you'll notice is usually a yellowish colour there. Sometimes there's not enough of it being made for you to see that colour though. So there's two tests we can use. One is we could add sodium hydroxide, which I've got there. And when I add a few drops of sodium hydroxide, the iron precipitates out as basically rust. So you can see that orange, you can call it rust coloured if you want to, but that orangey brown solid being formed. So you don't have to do a balanced equation for this in your internal, but I do want to show you what's happening, because this is good chemistry for you to know for the future. So if it was Fe3+ being made, the Fe3+ is reacting with hydroxide to become this, and this one here is a solid. FeOH3 is a solid. Okay, it isn't rust, by the way. It looks a bit like rust, but it's not rust. Rust has got a bit more happening than that. Okay, it's a bit more complex than that. And that is our orange precipitate, or orange-brown precipitate. Okay. The other one's actually a much more enjoyable experiment to do. I think it is anyway. So again, we'll put some Fe3+ in here. And for this, I'm going to add a couple of drops of a different chemical called potassium thiocyanate. Fe3+ is quite an awesome thing. It can make things called complex ions. And this is a complex ion being formed in here now. And you'll see that it went a blood red colour. Okay, so the colour of blood, basically. And that's what we call a complex ion. This is probably the best test for Fe3+, because there are other orangey brown precipitates with hydroxide. So this is our best test. So if in an internal, or anything actually, where you're using potassium thiocyanate, which is KSCN, you know you're testing for Fe3+. Again, you don't need to know the equation I'm about to write up, but it's, again, good chemistry to know. Primarily for our next topic, actually. So you notice I've taken the K out. Potassium ions are always spectator ions in what we're doing. Okay, so I'll take it out. Because it's K+, the rest of it must have a negative charge. You don't need to know this, but this is what we call an equilibrium reaction, which means it has arrows that go both ways. We'll learn about that in the next unit. And it creates, this is really easy to do, it creates this thing here, which is actually described as blood red. And the reason it's blood red is because of the Fe3+. Fe3+ is found in the middle of your hemoglobin molecules. It is the heme, it is part of the heme group. So it's complex formation that it makes is what gives your blood its colour. So Fe3+ complexes are often blood red. So that's why it's that colour. Alright, so that's Fe3+. If you're working with iron 3+, your two possible things are sodium hydroxide, which makes a rust-coloured precipitate, or browny, orangey brown, or however you want to describe it. Or you could be reacting with KSCN, the thiocyanate ion, and that will make it go blood red. Those are your confirmations. So if you're discussing justifying why you know that it went to Fe3+, not to iron, you've got two observations. One is you didn't see flecks of iron in there, so black or grey solid, but also when you reacted it with whichever chemical you decided to use, you got the expected result. Okay. Another one, you might be working with iodide. Now, iodides are not always involved in redox reactions, so we have to be a bit careful with that. But if iodide does undergo oxidation, it becomes iodine. Oops. So if it does undergo it, we get this happening. All right, this oxidation reaction. How could I confirm it? Well, the nice thing is iodine solutions are a similar colour to iron, actually. They're just a little bit darker. So they're a very similar colour. All right. So this is an iodine solution we've got here. However, you might have a reaction with iron 2 plus as well and go, I don't know if that colour is being caused by iodine or by the iron. Okay. So of course you've got to test for iron that could prove it, but you've got another one. In biology, iodine is used as a stain for cells because what it does is it binds to the starch, to the complex carbohydrates in the cells to be able to see certain parts of them. As well as that, if you're testing unknown things in biology to see which food groups they contain, if it contains starch, it'll go blue-black. Whereas if it contains any other complex carbohydrate or simple carbohydrate, it'll stay a brown colour. So in chemistry, we do the opposite. Biology use iodine as a test for starch, so therefore we'll use starch as a test for iodine and get this result. That goes a bluey black colour, a bit like ink. Okay, so we get that. So that's a really useful one for us to know. If iodine is a product, or could be a product, you'll be asked to use starch indicator to prove that. So I'm not going to give you the chemical reaction behind this because it's another complex formation, it's making another complex. But this stuff is blue-black. Oops. Goes blue-black if I add starch indicator. Alright, so if you're seeing something in your chemical reactions that have iodide involved, or iodate actually, if you have iodide involved and you're being asked to then test it with starch, you're looking for that blue-black colour. If it doesn't go blue-black, it means that that iron wasn't involved. Okay, it was the other iron that it's attached to that was probably involved. Okay. Right, next one. So we had a look at Fe3 plus forming a forming a precipitate with sodium hydroxide. What if you've done a reaction with iron? You've reacted iron with something, and you're not sure whether it became Fe2 plus or went all the way to Fe3 plus. So iron can actually go, strong colour, iron can be oxidised just to Fe2 plus, or it can go all the way to Fe3 plus if the oxidant is strong enough. So it can go all the way to 3 plus. Now this is not in your little table that you were told to learn off by heart. The point I'm making here is it becomes this first, but then if the oxidant is strong enough, it carries on to this. So I combine the two equations together to make this one. Okay. So I've not put the right number of electrons there either. I was going to make that 2 plus. So it can go all the way through. So how do we know? Well, again, we need to think we could use one of those two tests to prove that it went Fe3 plus. But what if they're both negative? What if it didn't go blood red? You can't just say, oh, that means it made Fe2 plus. That's not good enough. So what I've got here is an iron 2 plus solution, which I know has oxidized a little bit. So there will be a little bit of Fe3 plus in here. Actually, might use quite a bit of it. And I'm going to add sodium hydroxide to this. If it goes this way, a lot of it is oxidized. If it doesn't, you'll see what happens. Now you notice I'm not going to shake this one. Yeah, good, it worked. Okay. The colour of the stuff forming at the bottom is a green colour, a dark green colour. Alright? So that must be a different iron hydroxide. It can't be this iron hydroxide because that's the colour of rust. So it must be a different one. So it means that this has happened. Fe2 plus You'll notice I'm using sodium hydroxide but not writing sodium. Just like potassium, sodium, for the chemistry we're doing at the moment, is always a spectator ion. Always. Okay, so in this one, just that one hydroxide difference, therefore that different oxidation state of iron, gives us a completely different colour. Okay, so that's a really good test for that. Right, nearly done with this. We've only got one more that I really want to look at. Here I've got sulfuric acid. Now, if sulfuric acid reacts, it could be the sulfate or it could be the hydrogen being involved. Okay, so you might be asked to see if the sulfate is still present. Or you might have been working with a sulfite solution or sulfur dioxide solution, and we'd expect that to make sulfates. So we need to prove that sulfates are present. The chemical we use to prove that sulfates are present is anything with barium in it, so barium nitrate or barium chloride, because barium sulfate is insoluble. Okay, and next you'll teach you that it's sparingly soluble, but for this we say that it's insoluble. So add a few drops and look at that, it goes cloudy straight away. So if you're asked to add barium to something, then it means you're testing to see if any sulfate ions are present. That's our test for sulfate. Okay. So if you started with one of those two things, a sulfite or a sulfur dioxide solution, you could predict that it's going to make these, but you still have to confirm that it has, because you won't see any colour change. You won't see anything. What you need is you need barium ions, either as chloride or as nitrate. And that looks silly to write like that. All I'm saying is the two ions go together, aren't I? Not quite. What this is saying is that I've probably put subscripts here, aqueous, and solid. When I put them together, what I'm saying is that it's a solid. Okay, so that's where your chemistry is going to get to by the end of this year. But when you write it like that, that means a solid. When you write it like that, it means it's a solution. Okay, so the two ions in solution, which you saw me put together, became a solid. Okay, and then by the by, it also would have made hydrochloric acid in there, because I had sulfuric acid, H pluses, and barium chloride, so chloride ions. So it'd be that plus H plus Cl minus, if you wanted to do the whole equation. So you'll notice I'm also taking what's called spectator ions out, the one that's not involved in redox. It just makes writing the equations a little bit easier to do. Alright, any questions on that before we stop the video? Okay, so there are your really important ones. Just ask that when our filmer stops, they can take a photo of that as well, please.